Hi everyone and good day. I'm Xuesheng from BASiC Semiconductor. First, I'd like to thank Bodo's Power Systems for organizing such an inspiring event. It's my great pleasure to be here and I'm very grateful to have the opportunity to share a few things about an interesting research project going on here at BASiC Semiconductor. We are now entering the wide bandgap era of power semiconductors. For power electronics to further evolve, the power switches need to operate at higher frequencies. This demands the replacement of silicon bipolar high voltage devices by unipolar wide bandgap power devices. More specifically, at higher voltage range, we found silicon carbide devices are becoming increasingly popular. Compared to silicon IGBTs, silicon carbide MOSFET feature better switching performance, better thermal performance, and some avalanche capability. However, silicon carbide MOSFETs are not so good under short-circuit conditions. They're more expensive, and due to high defect densities on wafer material, it's more difficult to fabricate a large chip for high current rating. That leads to the next question. Could we split the tasks of power switches and assign different types of power device to better accomplish those tasks in terms of cost effectiveness? There has been quite a few hybrid solutions from the industry. A commonly seen solution nowadays is to use silicon carbide diode as the freewheeling diode for the IGBT. Due to the considerable reduction of diode reverse recovery, this has been a very cost-effective solution on the market. For the role of power switch, often silicon carbide MOSFET is used in parallel to silicon IGBT. This general idea is not entirely new. Similar solutions using high-performance silicon MOSFET appeared almost 20 years ago. Here, the configuration of silicon IGBT and silicon carbide MOSFET is determined mostly by the trade-off between conduction loss, switching loss, and cost. As far as we know, existing solutions from industry switch the two devices simultaneously. So we have been thinking, how can we go one step further? We tried to split the switching and conduction tasks even more. That is, in general, use silicon IGBT only for conduction and silicon carbide MOSFET only for switching. This is an attempt to accomplish those tasks at a lower device cost. Using specialized control scheme, higher switching speed is possible. Also, silicon IGBT can be used to compensate the limited short-circuit capability of silicon carbide MOSFET. And silicon carbide MOSFET can be configured to enter avalanche earlier than silicon IGBT. In addition, for serializing and paralleling operation, the use of silicon carbide MOSFET can provide easier active control of voltage and current. Our latest work in progress is based on some of my early research. For example, here for the turn-off, the load current is first transferred from the silicon IGBT to the silicon carbide MOSFET. As the high-level excess carriers accumulated in the on state in the IGBT recombined and diffused before the turn-off, the DVDT of the device pair can be increased and the losses can be reduced. Here, as the thermal allowance of the silicon carbide MOSFET in a switching cycle is fully dedicated to switching, the current spec of the silicon carbide MOSFET can be further reduced from existing hybrid solutions to achieve lower device cost. Of course, multiple SOA of the silicon carbide MOSFET require in-depth studies to make sure that such a control scheme is operational. Here is a comparison of the conduction characteristics and the switching energy between silicon IGBT and the silicon carbide MOSFET of similar specs. Referring to the figure on the right for switching, clearly silicon carbide MOSFET possesses advantages regarding the switching energy. Therefore, assigning the silicon carbide MOSFET to the switching task is an obvious choice. Referring to the figure on the left for conduction, at high conduction current, the IGBT has a lower voltage drop due to conductivity modulation, but because of the additional p-n junction on the current path, a crossing point exists, where the silicon carbide MOSFET has the advantage. Therefore, for low load current, using silicon carbide MOSFET for current conduction can further reduce the overall losses. Based on this principle, to maximize the trade-off between overall efficiency and device cost, control scheme can be tailored for specific applications. For example, for interleaved boost converter, at very low duty cycle, we can only use silicon carbide MOSFET to reduce the conduction loss. And at normal duty cycle, we can switch in the silicon IGBT. For resonant type converter, at heavy load, silicon IGBT can be used together with silicon carbide MOSFET, whereas in light load, we could only use silicon carbide MOSFET. Similarly, for totem pole PFC, within one AC period, when the IGBT VCD is below the crossing point, we can only switch in the silicon carbide MOSFET to reduce losses. And when the IGBT VCD is beyond the crossing point, we switch both the silicon IGBT and the silicon carbide MOSFET for maximum current conduction. Of course, to implement those control schemes, additional controller modules are essential. First, we need to sense the load conditions and the device conditions. These provide the fundamental control inputs. Also, fast device and circuit models are required to build the feedback controller which is capable of fast control response. In addition, protection strategy and device configuration can be complicated to avoid the disadvantages of each device. To sum up, hybrid solutions are certainly attractive to achieve better performance in high power applications, provided that the controller-related circuits can be efficient in terms of speed, precision, and cost. Thanks everyone for your attention, and once again, thanks Bordeaux Power Systems for providing such an excellent opportunity.